Welcome to this lecture on statistical process control. Imagine you are driving a car down a straight highway on a windy day. You naturally make tiny adjustments to the steering wheel to stay in your lane. These small wiggles are normal. But if a tire blows out, the car swerves violently. Statistical process control is exactly like being the driver of a manufacturing process. It helps us tell the difference between normal, everyday wiggles and massive, unexpected problems. Let us dive in and learn how to keep our processes safely on the road. Now that we understand the driving analogy, let us look at the formal definition. Statistical process control, developed by Walter A. Shewhart in the 1920s, is the application of statistical methods to monitor and control a process. The core idea is that variation exists in everything. No two manufactured items are ever exactly identical. Shewhart divided this variation into two categories. First, chance causes or common causes, which are natural, unavoidable background noises like minor machine vibrations. Second, assignable causes or special causes, which are unusual shocks to the system, like a broken tool. Our goal is to detect these assignable causes quickly. Building on the idea of detecting assignable causes, we use a primary visual tool called the control chart. This chart plots data over time against statistically calculated limits, acting as the edges of the highway for our process. We calculate three main lines based on historical data: a center line representing the average performance, and an upper and lower control limit. These outer limits are typically placed 3 standard deviations away from the average. Because a standard deviation measures how spread out data is, placing limits 3 standard deviations away captures nearly all natural expected variation. Let us look at the fundamental mathematical formulas that define these boundaries, starting with the center of our control chart. The formula is CL equals mu. Conceptually, this line represents the historical average of the process over a long period. The symbol CL stands for the center line, which is the target we want to hit. The symbol mu represents the true mean or average of the process data. By plotting this line, we give machine operators a clear visual target. If the process is perfectly stable, the data points will cluster evenly around the center line. Now that we have a center target, we need to calculate the maximum acceptable boundary for our data. The formula is UCL equals mu plus 3 times sigma. This formula finds the upper boundary by taking the average and adding 3 times the standard deviation. The symbol UCL stands for the upper control limit. The symbol sigma represents the standard deviation of the process, which measures the natural spread of the data. If the standard deviation increases, this upper limit moves higher, widening our acceptable zone. Any data point falling above this line indicates a severe problem has occurred. Just as we have a maximum boundary, we also need a minimum acceptable boundary. The formula is LCL equals mu minus 3 times sigma. This formula finds the lower boundary by taking the average and subtracting 3 times the standard deviation. The symbol LCL stands for the lower control limit. Together with the upper limit, this creates a safe zone for the process to operate within. If the standard deviation decreases, this limit moves closer to the mean, tightening the safe zone. If a data point falls below this line, the process is experiencing an assignable cause of variation. Before we move on to visualizing these limits, we must explicitly define a critical difference that confuses many students. There is a massive difference between a process being in control and a process being capable. When we say a process is in control, we strictly mean that it is stable, predictable, and only experiencing natural chance causes of variation. All data points fall safely inside the control limits. However, capability refers to whether the process can meet the customer's specific requirements. You can have a highly stable process that consistently produces parts that are entirely the wrong size. Understanding capability is crucial, but it is also vital to understand how a process signals trouble on the chart itself. A single point falling outside the control limits is not the only way a process signals an issue. Abnormal patterns within the limits also signal a loss of control. For example, if 9 consecutive points fall on one side of the center line, the process average has clearly shifted, even if no single point has crossed the upper or lower boundaries. These abnormal patterns indicate that an assignable cause has entered the system and changed its fundamental behavior. Let us see everything we just discussed in a visual format. Here you are looking at a basic statistical process control chart. The horizontal axis represents time or the sample number, while the vertical axis represents the measured value of our product. Notice the solid green line in the middle? That is our center line, or mu. The dashed red lines above and below are the upper and lower control limits. The blue line connects our data points. As long as it bounces randomly between the red lines, we are stable. But look at that red dot piercing the upper limit. That is an alarm bell, proving an assignable cause has disrupted the system. Now that we have seen the diagram, let us apply our formulas to a concrete example. A factory uses a machine to fill bottles with exactly 500 milliliters of water. Historical data shows the process is stable, with a true average fill volume of 500 milliliters and a standard deviation of 2 milliliters. We are asked to calculate the center line, upper control limit, and lower control limit. We start by defining the center line. We substitute our known process mean into the formula, setting the center line mathematically at 500 milliliters. This is the ideal target volume the machine aims for continuously. Continuing with our filling process, we now calculate the upper control limit. We write down the formula, which adds 3 standard deviations to the process mean. We substitute our known values. The average of 500 replaces the mean symbol, and the standard deviation of 2 replaces the sigma symbol. We perform the multiplication first, multiplying 3 by 2 to get a total spread of 6 milliliters. This represents the maximum natural upward drift we expect. Adding this to our target average gives us 506 milliliters. This is the absolute maximum volume a bottle should contain under normal conditions. Finally, we calculate the lower control limit to establish the safe flow for our data. We use the formula that subtracts 3 standard deviations from the mean. Substituting our historical values, we insert 500 for the average and 2 for the standard deviation. Multiplying 3 by 2 gives us the 6 milliliter downward spread. Subtracting this from 500 gives us a final answer of 494 milliliters. Physically, this means as long as the machine fills bottles between 494 and 506 milliliters, the process is behaving normally and is in control. With our limits established, let us see how an inspector uses them in real time. Using the same water bottle filling machine, a quality control inspector takes a new sample from the production line. The measured volume of this newly filled bottle is exactly 508 milliliters. We need to determine if the process is still in statistical control or if an assignable cause has occurred. We assign the variable x to a measured value of 508. We then recall our previously calculated upper control limit, which was mathematically established at 506 milliliters. Continuing our inspection, we must mathematically compare our new sample against the established boundaries. We place the two values side by side to test the condition. We can clearly see that our sample measurement of 508 is strictly greater than the upper boundary of 506. Because this inequality holds true, the new data point has breached the established limits. Our final conclusion is that the process is officially out of statistical control. Physically, this tells the factory manager that a specific assignable cause, like a stuck dispensing valve, has occurred and they must immediately stop production to fix it. Now that we have successfully used these formulas to detect a problem, let us zoom out and understand why this matters so much. Statistical process control is the absolute backbone of modern manufacturing and quality assurance. Without it, factories would have to inspect every single item they produce, which is incredibly expensive, time consuming, and often impossible if the test destroys the product. By using SPC, companies can monitor just a small sample of products and use mathematics to guarantee the quality of the entire batch. It prevents massive waste and ensures customers do not receive defective goods. We have covered a lot of ground today, so let us review the most important ideas. First, statistical process control is a powerful mathematical tool used to monitor process behavior and distinguish between normal background noise and serious system errors. Second, by calculating control limits based on historical data, we create clear mathematical boundaries for acceptable variation. Finally, always remember that a process can be perfectly in control without being capable of meeting customer needs. You now have the foundational knowledge to understand how data is used to maintain high quality production in the real world. Great job!